Greetings. This is the second media computation video. This one's relatively short because we've done all the interesting things with pictures to introduce things. Now I just wanted to do sound, and we're not going to do much with sound this term, but I wanted to introduce it so that we could be able to compare pictures and sound later on. So same learning goals, except we're down here to how do digital sounds work. So sound. So the other half of the media that we're going to explore is sound, which includes speech, music, synthesizer sounds, natural sounds, pretty much everything that you can hear. So the first question is, what is a sound? And so you have any object that can produce a vibration in matter will make a sound. There has to be a transmission medium. At least here on Earth, the transmission medium is the air that makes a sound, which is why all those science fiction movies that have spaceships blowing up in space and making noises are just wrong, because there's no transmission medium in space. Anyway, the way that sounds work is that the source of the sound will vibrate and cause air molecules to vibrate, and those air molecules will produce what's called a sound wave. It's an analog wave that impinges on your ear. These sound waves have two characteristics. The first is the pitch of the sound, and this pitch of the sound is based on the frequency of the cycles in the sound wave. The distance from the top of this wave to the top of this next one is one cycle. So this is one cycle here, and the number of cycles that you get per second, also called the number of hertz per second, gives you the frequency of the sound, and the pitch is based on frequency. The smaller the distance, the higher the frequency, the higher the pitch. Then the other characteristic of sound is loudness, and loudness is based on the amplitude of the wave, how high the wave is, that's, you can imagine that there's a zero line right about here going through this sound wave, and these are above zero and these are below zero. But what we're concerned with for loudness is the total height of the wave. Okay, so the two basic characteristics of sound are frequency and amplitude. All right, so how does our hearing work? And the way our hearing works is high school biology. The sound is trapped by our ear. Our ear catches the sound and funnels the sound through our ear canal down to the eardrum. The eardrum then vibrates, and it vibrates in exactly the same frequency and amplitude characteristics as the sound does, the generator does. There's a whole bunch of complicated stuff that goes on in here with all these little bones and everything. The bottom line is, at some point, the sound gets to your inner ear, where the vibrations are translated into electrical energy and sent down the auditory nerve to your brain, and you actually hear what's going on. And so that's how you hear stuff. So it's all a matter of vibration and frequency and amplitude. And all of those things can be characterized by numbers, which is convenient because since we can do that, we can then store these sounds inside the computer. So how does recorded sound work, and is it different? Well, recorded sound is fundamentally the same as the sound you hear in the air. There are just two different ways of storing the sound. For phonograph records and old-style recordings like that, they capture the sound continuously, and they reproduce the analog wave signal that was used to create the sound in the first place. If you took an old vinyl record If you looked at it closely, you'd see the grooves in the record, but if you took a microscope to it, you would see that the grooves are all of different heights. And it's the up and down motion of the needle at the end of the armature here that changes that's converted to electricity that is then converted back into sound at the speaker. But it's all strictly an analog operation. CDs don't work that way. CDs, DVDs, computers, what they do is they can't represent the analog signal. CDs, DVDs, and computers are all digital devices. They only have ones and zeros. And so what they have to do is they have to take that analog wave and they have to measure the wave at certain points in time. And so if we go back a couple of slides, what a CD maker will do is it samples the wave at different times, and it produces a number which is a representation of the height of the wave at that sample time. And so if you only have a very few samples, you're not going to be able to reproduce the analog wave very well. But if you have lots of samples, thousands and thousands of samples per second, then you can approximate the shape of the analog wave very closely. And that means you can then approximate the sound very closely. So that's how digital recording works. For CD, what's known as CD quality is 44,100 samples per second. And you go, what the heck? Why? Where did they get 44,100? Well, this is based on a theory in physics called Nyquist's theorem. And what Nyquist's theorem says is the maximum frequency that you can represent in a digital sample is 1/2 of the number of samples that you take. And so humans can hear noises and sounds up to about 22,000 cycles per second, or 22,000 hertz, or 22 kilohertz. And because of that, then, we have to sample at a rate of 44,000 samples per second in order to be able to reproduce accurately the sound that we have in the analog sound. And so that's what Nyquist's theorem tells us. So Nyquist's theorem tells us exactly how many samples we have to take in order to be able to reproduce the sound correctly. Okay. So why do we want to digitize sound? Aside from the obvious that you can't store the analog sound in the computer, there are other reasons to digitize sound. One is high fidelity. The higher the number of samples that you have, the closer you are to the original sound, and so you get a very, very good reproduction, a very high quality reproduction of the original. But then the second reason is, and this is the bane of the existence of every record company on the planet, perfect reproduction. Because when you store the sound, you store it as a digital file. You just store it as a series of numbers, which is the height of the wave at each one of these samples. In order to make a copy, you just have to copy the file. And the copied file is a perfect copy of the original file. So it sounds the same every time you make it. This is not the case for typical analog signals. If you've ever made a copy of something on a cassette tape, for example, you probably haven't, but I used to, because I would rip vinyl records and record them onto cassette tapes to make a mixtape. And But if I then wanted to have one mixtape for my house and another mixtape in my car, I would have to make a copy of the copy I had made, and the second copy was not as good quality as the original. That's not the case with digital recordings. You make a copy of that MP3 file, it's exactly the same as the original, and it will sound exactly the same. And it's also, of course, with computers, it's much easier to make copies than it is when you're using analog stuff. So perfect reproduction is really the reason that people like to digitize sound, particularly music. It's also easy to transmit. You can run it over the internet. You can download it as data. You can stream it. It's a piece of cake. And it's also easier to manipulate. It's just bits. So it's just numbers on the computer, so it's very easy to manipulate the sounds if you want to make changes to the recording, which is sort of the bane of lawyers, because you can make changes to the recording itself. Okay, and then my favorite is that you can encrypt the sound at one end, transmit it, and decrypt it at the other end so that you can have secure speech. So you can, Skype does this and other programs do this. You can speak at one end. Your speech is sampled and digitized. It's then encrypted, sent over the internet, decrypted at the other end, and then pumped out through a speaker. And in between, anybody who intercepts the speech, unless they have the key to the cryptographic algorithm, cannot understand what was being said. All it'll get will be gobbledygook. So that's also very, very handy. That's very, very difficult to do with analog. It's a piece of cake to do with digital stuff. So in Java, how do we do this? Well, it's the book classes package gives us similar tools for sounds as for pictures. So, for example, I can say string fname equals file chooser dot pick a file, and I can pick a file. And so let me go down here to my Dropbox folder, and we'll go to media sources. And somewhere down here, I have a music. And somewhere down here, I have an end of the world clip. Okay, and so I've done this. I can do the same thing I did before. We can print the name, and then it tells me exactly where the file is. By the way, for the book classes stuff, you can't use MP3 files because they're compressed. You have to use WAV files, which is a Microsoft technology, which is now everybody can use. But it's an uncompressed sound file. And so you do that, and so now we can make a sound by saying sound. There's a sound class in the book classes jar. SND1, actually just call it SND, equals new sound fname. And now I have a sound. I can try printing out that sound, just like I've tried printing out the picture. Oops, not sound. System.out.println SND, and it tells you it's a sound file, and it tells you it has 176,400 samples in it, which means it's only a few seconds worth of it's only 3 or 4 seconds worth of sound. It's just something that I ripped out of a song. And so now to play that sound, I can say sound.play, and I get semicolon, I get. And just about 3 seconds worth of song. And of course I can do it again. Because I've made that sound and I made the file, I can just play it over and over and over again. And later on, I'll show you how to make changes to the sounds, so you can make it sound like Donald Duck or Barry White or different people like that. That's about it. That's all we're going to talk about in terms of sound right now, but we'll come back to it hopefully sometime later in the term. So the next video will be more about pictures, and we'll really start to work with pictures starting in the next video. So have fun. Thanks for listening.